ChatGPT is judging the intelligence of the person asking the questions. Deep question, I'll think of a deep answer. Or a silly question, I will give a silly answer. In other words, it's in a sense a mirror. Everybody compares it to humans, and I think that's the wrong way to think about it. It's a tool, it's like a shovel, and you have to know how to use the tool properly. But if you do, you can actually dig much deeper than you could with your hands.
Welcome back to the Into the Impossible podcast. Today we are exploring the nature of minds, brains, and even whether or not these new and impressive tools like ChatGPT are actually doing thinking. And I'm joined by a good friend of the campus and of all of science in particular, Dr. Terry Sejnowski of the Salk Institute, and also a joint appointment at UCSD, neurobiology, right?
That's correct.
Good. And we have a lot of friends in common. Andrew Huberman, Gentry Patrick, both. Gentry was a guest on the show. I'm trying to get Andrew on maybe for his new book. Today, we're talking about your books, and I have two of them. This one, I'd wanted to have you on, The Deep Learning Revolution, which was really prescient, and it did kind of presage a lot of the stuff that we're talking about today in your new book, and that everybody's talking about, and that's ChatGPT. So I'd like you to do what you're not supposed to do, which is to judge a book by its cover.
Okay.
So the title, subtitle, and the cover art.
Well, first of all, let me say that the MIT Press gets awards for their art. They're very, very design and high quality paper and that sort of thing. So the background design actually mirrors the one for the first book.
Yeah.
If you look at the cover, and it's kind of a abstract version of a brain, which is where we are because of the fact there's a convergence going on between the scientific study of how brains work, but also now creating AI, and that's an engineering problem, are now using the same mathematical framework. And so this is it's a great opportunity for exchange of ideas, concepts, and now we have these ChatGPT and other large language models, which we don't understand how they're able to accomplish all the different things that we ask them to do.
The book is sort of a interesting, almost like a collaboration with AI, which is something that we tell our students not to do. But you kind of envision and interact with ChatGPT throughout the book. So tell us about that. What led you to choose that sort of format?
So as I was going through and writing the book, what I realized is that, people learn with concrete examples. I mean, and also with the things that they may have heard about, and I wanted to actually give these concrete examples in the form of a dialogue that I had. And I was actually, what inspired me at the beginning was an article I read in The Economist, which was before ChatGPT was public. It was available to academics. And the article was talking about it and asked two different people, do a dialogue and come up with their conclusions. And I'm not going to give names here. I'm just going to say that one of them was based on a theory of mind. And this is the idea that I understand how other people's minds work. And that's why you can make predictions about things that, are very, very abstract and having the social issues and so forth. What does another person understand about something and whether they see it or not? In any case, it passed the test. And that was amazing because we, at that time, no one really understood what the real capabilities were. And the other person, these are both very distinguished people, by the way, asked questions like, when was the Golden Gate Bridge taken across the
Nile River, or the Golden Gate?
The desert, the Gobi Desert.
Yeah,
and the answer it got back was, October 2nd, 1964. And questions like that made the response of that particular dialogue was that it was clueless. In fact, it had no clue that it was clueless, right? Mm-hmm. And so here's these two extreme conclusions. It was a puzzle. I mean, how could that be? And I finally traced it down to the prompt. Mm. So the prompt is what you ask the ChatGPT to do, as you know. Yeah. And by modifying the prompt a little bit, I was able to figure this out. I said, I wanted to repeat exactly the questions that the second person gave it, but I also in the prompt said, if it's a nonsense question, say nonsense, right? And now I gave it exactly the same questions, and it came back nonsense for each one. So it clearly what's going on here is that you ask it a stupid question to get a stupid answer. In fact, it's kind of playing with you, right?
Mm-hmm.
So, and then I trace it back to another concept, which is the fact that it can take any persona because it's been trained on the world's knowledge base and, novels, newspaper articles, computer programs, right? And so it can take any one of those persona. You could ask it to write a short story in the style of Hemingway, and it will, right? It can take that persona. So you have to tell it what persona you wanted when you're asking it questions.
Mm-hmm.
And now it's elementary. Everybody knows that. But back then they didn't. And so if you jump in with, like I say, a question that is in the ether, you don't get any reasonable answer because ChatGPT doesn't know. And I call this the reverse Turing test.
Mm-hmm.
Turing test is a human to judge from the responses whether or not you're interacting with a human or an AI, right?
Yeah.
Well, ChatGPT obviously passed that test long ago, right?
Some say it has. Some say it's yet to pass it, but
I think that this is as close. If you were the bar can always go higher. Okay?
Yeah,
but
right.
Right now, I would say for most people, it's pretty close.
Mm-hmm.
So here's what I think is happening, which is that ChatGPT is judging the intelligence of the person asking the question.
Mm.
In other words, is this
it's training
a
us.
deep question? Oh, I'll think of a deep answer. Oh, is it a silly question? I will give a silly answer. In other words, it's in a sense a mirror. I call it the mirror hypothesis.
Yeah.
And I have a whole chapter on the power of the prompt. So this is now everybody knows that you have to have a lot of practice, and you just can't use it out of the box. You have to really understand how to use it.
Yeah, they were talking recently about prompt engineering as a subject we might teach in the engineering school, and I thought that had to do with like how close to on time are these engineers really? They have to be prompt. It's a sign of a good character. But no, in reality, I think that is correct. And I wonder to what extent are they training us? Are these transformers transforming us in the way that we think, maybe not to the level of, Homo Deus or whatever people kind of conjecture, but, is there this feedback iteration process in which case there's some level of maybe collective memory and sentience that's using their skills to improve our ability to interact with them. And you and I both know teaching a graduate course is sometimes more enjoyable than teaching, 101 or 100 or one level. Here we have one level because it's closer to our level of comprehension. And sometimes the students teach us things. So can these things help us? Will we be modified, or are we already getting modified by these guys?
Well, my first book, I conjectured that the deep learning revolution was going to make us smarter. That is to say, make us more able to solve more problems faster, be more productive. And I would say that that's pretty much played out in the sense that a lot of people are now using it. And, like computer programmers, it's actually almost universally used now to do kind of the basic outline of the program and saving a lot of time. And it really is now the way to think about this. Everybody compares it to humans, and I think that's the wrong way to think about it. It's a tool. It's like a shovel, and you have to know how to use the tool properly. But if you do, you can actually dig much deeper than you could with your hands.
Yeah. That's a great analogy. I think of it as a tool like a lawyer. It's incredibly smart, but it's incredibly expensive if you don't ask it the right things. I mean, you can ask a lawyer to review your kid's homework and they'll charge you $575 an hour. It's not a great use of the time. But I wonder, just to push back with respect on that concept of enhancing us, to date, most technological advances have made us worse off as a species. I'm thinking about, I can remember my childhood phone number, in my home in New York in Westchester County. I can't remember, my best friend's phone number, who lives around the corner. I don't know Gentry Patrick's or Andrew's numbers. I just don't remember them because I've outsourced that to a pointer in my brain and onto my phone to know where to look. Similarly, directions. I'm actually a private pilot. I fly, little Cessnas around. And we call it being the child of the magenta line. You get in the plane, you take off, you push autopilot, and then you sync to the navigation heading, and you get this magenta line that takes you where, and it can do the most complicated things. unheard of decades ago. But it's made me less capable as a dead reckoning. I used to be able, I flew all the way once from El Monte Airport in Pasadena to Santa Monica without refuel. No, but in all seriousness, I could do much greater, airmanship, we would call it, or dead reckoning. Or now I can't do it. I got GPS on my phone. I never do it. So is this the first case of technology making us better?
Well, you point out something really important, which is that when we start using tools, we become dependent on them. And also, all new technologies have both benefits and risks. And so maybe the loss of abilities like that, like map reading or dead reckoning, might be one of those that you might lose. My guess, though, is that you would come back really quickly if you had to, right? I mean, if you were needed it really.
A couple of Carrington events.
Yeah, it's somewhere in your brain, but the problem is recall. But here's an example. Okay, so do you remember when hand calculators were first being sold? They were very expensive, HP calculators. Mm-hmm. And I remember everyone saying that, now nobody's going to learn arithmetic anymore, right? They're just going to use their calculator. And I think that, we still teach arithmetic in school, and it's important to get an intuition for numbers, numeracy. So, there's actually a movement now in California, as you may know, to get rid of rote learning, what they call rote learning, which is practice. Mm-hmm. So, memorize your multiplication tables. But I think it's absolutely essential as a foundation for being able to have a feeling for numbers, for being able to estimate orders of magnitude and so forth. The calculators have found their places when you've got a lot of numbers to add up that you're not going to do it in your head. I use it for that, but when I just have to order of magnitude something, and I do it in my head very quickly, at least to know if I'm close. And so, it's a two-edged sword, and I think that in the future, I think our children will be living in a very different world, and taking things that that we take for granted now, they'll be doing it in a completely different way. But that's always been that case. I mean, this is nothing new about it.
Right. Albert Einstein said he had what he called the happiest thought of his life, which is that an observer in free fall would experience no gravitational field. And that led to the notion of what we call the Einstein equivalence principle, which is underpinning the bedrock behind general relativity, which is how we navigate in 4 dimensions in space-time, and how GPS satellites do their work so accurately. But I wonder, and I always suggest that I'm not threatened by AI. I'm an experimental physicist. We just took a tour of my lab. I want to highlight that in a minute. But theoretical physicists, I'm even saying to them, you shouldn't be too nervous, because I don't believe that a computer system, any system, no matter how many GPUs it has, can viscerally sense what that sensation that we all know right now. Think about going on a roller coaster or on a plane and going over a bump, and you have that pit in your stomach sinking feeling. So can a computer visualize that or embody without embodiment, so to speak? And then second of all, what does it mean for a transformer to have a happy thought that Einstein said titillated him beyond repair? So what do you think about this, that we're safe, we have full employment prospects?
There was an article, a little essay in the New York Times by Noam Chomsky, who's a distinguished linguist. Yep. And it was his take on ChatGPT. Now, he's a linguist, and he actually put a lot of store in syntax as being kind of a core central to expressivity of language. And he's right, that infinite number of sentences, right, that we can create. And in any case, he was saying, no, these ChatGPTs, they sound like they know what they're talking about, but in fact, they can't think. They're not capable of thinking. Oh, wow. Okay, so he gives an example. Here's his example. Ask the following question. I'm holding something in my hand, and I suddenly open my hand. What will happen? Well, of course, everybody knows from experience that it will drop, right? Because you've experienced that. Right. Okay, let's ask a counterfactual question. What if there were no gravity? What would happen? Mm-hmm. Well, we know about space. It would just float away, right? And so, he was in a series of questions like that. And so I said, well, let's do an experiment. I believe in the experimental method. And so I asked the question to ChatGPT, what will happen if I am holding something and I let it go? It will drop down. And actually, the next question was, why did it drop down? And the answer comes back, gravity. Mm. And then I asked, if there's no gravity and I let it go, what will happen? Well, it will just float away. Mm. In other words, without ever having experienced gravity or any, experiment like that, no gravity, it was able to answer those questions. Now, at the end of his little essay about thinking, he said, that's thinking. And I basically showed that if that's thinking, then, well, it passed the test, right? So what's amazing is that without having any sensory experiences or motor output, it has completely gotten all this information and insights out of words. And in fact, it was trained on a very simple task just to predict the next word in the sentence. Yeah. And it's a lot of words, trillions of words. And it got better and better and better and better. And in order to do that, it developed inside of this very large network with trillions of parameters, weights, a neural network. It developed a semantic representation of the sentence. The only way you can answer sentences that are complex is to know what the words mean. They have multiple meanings in that sentence, in that context. And so it must have read a lot of stories about gravity or something that allowed it to be able to answer those questions.
I still feel like I'm safe, though, or my theoretical colleagues down the hall are safe. And I'll give you another example that I did with an undergraduate this past quarter. He's very bright undergraduate, Evan Watson. He's on the graduate school market. So anyone listening out there, I have a big EDU audience. Please be on the lookout. And we asked the following question. If ChatGPT, any LLM, Gemini, pick your favorite, or symbolic regression or whatever, was around in 1913, before Einstein came up with a retrodiction of why Mercury's orbit was so unusual, right? So the anomalous advance of the perihelion of Mercury's orbit, it's an ellipse, but it doesn't come back to the same foci every time, or same apsis, so the actual structure of the orbit precesses. And it precesses a minuscule amount. Actually, there's it's a large amount, but most of that's due to classical gravitational effects. And what Einstein showed is that a tiny effect, 5 or 6% effect, is due to the curvature of space-time that is produced by the sun. So we asked the following question. If ChatGPT was around in 1913 and had access to every single orbit of Mercury going back thousands of years, and we can calculate what its orbit was, retrodict what its orbit was. We just fed it to it, or LLM system. Could it come up with a necessity for curved space-time? And it just utterly failed. We had to, and I'm not saying we did.
Oh, you actually tried that?
We did this, yeah. So I can share with you my student's senior thesis. He's working on senior thesis now.
That's a nice test, yeah.
And so it was unable to do that. And maybe, we're not the best prompt engineers, or we're not the best, but we set it up. And there are people that have done this. Miles Kramer and the UK has looked at the similar types of question, where we've been conversing with them.
Well, did you prep it with the field equations, or?
Well, so if we wanted it to come up with, first of all, we wanted to discover that there's something anomalous just from the orbit, knowing what it knows about
just
orbits,
giving it numbers.
Keplerian, and then feeding in from JPL's Horizon database, we fed in, literally thousands of orbits of Mercury, both real, measured, from radar reflection measurements off the planet since the 60s to, before in ancient times. And we found we had to just kludge it by putting in a gravido, basically simulate gravitation using electromagnetic type forces. And the reason was it is essentially discretizing, and making this massive grid out of, space-time, but it doesn't know how to curve the points between space-time and represent them in a faithful way. So I'm not a doomer, I don't know what you call me. I'm an optimist. I love playing with these models and I enjoy it, and we're doing research with it. But the question of, can it come up with something novel? What you described is true. My 6-year-old can do that too. But I'm not saying, that's a bad question, or Chomsky's question, or whatever. But the point is, for something that's, you say to it, I want a theory of everything that unifies gravity and, go to it.
Right.
It seems to me the answers I always get is, well, it's not trained on sufficient data yet. And I always say, well, do we really need for the next Fast and Furious movie to come out to get a theory of everything? Like, it seems ridiculous.
Okay. No, fair enough. And so it failed on the general relativity test. But, that's a really high bar. Einstein is a really high bar. And I think that it's a little unfair at this point. Where are we with this? ChatGPT's only been around for a couple of years, right?
Sure. Yeah.
And we are at the stage of the Wright brothers on the very first flight. The first flight went 10 feet up and 100 feet forward before it crashed. There's a book out, biography of the Wright brothers. It's very well written.
Oh, McCullough? Or is it?
Yeah, McCullough.
Yeah.
Yes,
Yeah.
That's right. And one of the things that they had difficulty with is controlling it.
Yes.
Making it turn in the direction they wanted without crashing. And that turned out to be the very difficult problem. And it really required a different mechanical system. They were trying to curve the wings rather than put a flap on it. So what happened after that first flight was incremental advances that made it safer, go faster, and so forth. And interestingly, they were inspired by birds.
You show pictures in the book,
which were gliding with very little power. And then they put together a wind tunnel and tested airfoils for lift. And they were very serious. And they were able to actually create a good design. So one of the things that they looked at the feathers, right, and said, "This is amazing. It's very light, but it's very strong and it has a lot of area." So they used canvas over spars, which is a good way of doing it. The military at the time was building metal airplanes that, of course, crashed and burned.
Langley, famously.
Famously. What I'm saying is that often to get things off the ground requires ingenuity, entrepreneurs, and that's what we were back in the 80s. And then in order to be able to get something that actually can be practical requires an enormous amount of effort by a lot of people who are improving it, making it go faster. And back in the 80s, we didn't know whether it would scale. And now we know. It's 40 years later. We know that it scales beautifully, just like your brain, by the way.
Mm-hmm. There's the brain right there.
But the amount of computation required was absolutely enormous. Yeah, I mean, your brain is really amazing. It has 200 billion neurons. It has about 100 trillion synapses, which is vastly more computing power than we have right now in these large language models. But it only runs on 20 watts.
Yes.
So you don't need a nuclear power plant.
But it only processes at 10 bits per second or something like that. I mean, the visuals, obviously we're getting terabytes of data every second.
Yeah. Though this is actually a very interesting point, which has to do with matching the speed of processing to the speed of the world. I mean, the world doesn't work on the nanosecond scale, except if you're a particle physicist, right? But as long as the information can flow through the network fast enough and in parallel, you can do the computation in real time. And traditional AI never could do that, right? It had the von Neumann architecture, and going parallel, massively parallel with a very high degree of interconnectivity. And the secret sauce was learning all the parameters, the weights between the units, which are like neurons. That really turned out to be the architecture that got us to where we are today in modern AI.
Yeah, and you played a big role in that with your colleague, Jeff Hinton, who just won the Nobel Prize, and you were just in Stockholm to celebrate that.
I was. It was magical. I really was unbelievably dramatic, I would say. The way that they presented it, just everything was perfect. It was, in fact, you couldn't get in unless you had white tie and tails.
Yes. Well, I won't ever be able to get in after my first book, losing the Nobel Prize, which is kind of an assault on some of the lacunae that I find with it. But that's beside the point. So talk about that. The reason why you were invited. I mean, it's because it wasn't because you're family with them. You actually and Jeff and right. It's played a huge role in the initial development, not only of of I want to make sure that people understand your contributions, not only to, neural network but also like parallel computing. I mean, you made really fundamental research contributions, and it's curious to me always why you're at the Salk and not in, the engineering department. So talk about those issues. How did you come to land at Salk, and how did you come to land in Stockholm?
Okay, well, long story, but I started in physics, and got a. I worked actually. My master's degree is with John Wheeler on relativistic astrophysics, so I have a little bit of background there. But then my PhD is with John Hopfield, who was one of the Nobel Prize winners, and it was early days, and there wasn't a lot of work, computational or theoretical work in neuroscience. It was very empirical. But I thought that we could, help with trying to extract out some interesting new insights from the data that was being recorded one neuron at a time from the visual system, for example. That's how I started thinking along those lines. And just at the time when I was I figured that I really need to know more about the brain, right? So I did a postdoc actually at Harvard Neurobiology with Stephen Kuffler, who is a very famous neurobiologist. He's really one of the founders of that field. And I realized the complexity of the problem. The brain is incredibly complex at every level. From molecules all the way up to the behavior. It's really, really evolved by hundreds and millions of years. It was at that time that I met Jeff at a meeting. It was a meeting he organized here in UCSD. He was a postdoc there. I was a postdoc at Harvard, and it turns out we both had the same intuition. We were both interested in neural networks. We were both interested in AI. Here's our intuition. The only existence proof that any problem in AI could be solved was that nature had solved them. And so we decided to take a look at how that was done. And really what we were interested in is the architectures and the algorithms. The architecture, as you know, is massively parallel, a lot of interconnections, and the secret sauce is learning. And that was something we wanted to really develop that and scale it up. But at the time, computers were really slow by today's standards, and memory was very expensive. And so progress was slow. But we did something which was really quite remarkable. And it was probably, at that time, I was an assistant professor at Johns Hopkins in biophysics, and he was an assistant professor at Carnegie Mellon University in Pittsburgh in computer science. And we heard John Hopfield give a lecture, which was about his Hopfield equation and some recent work that he had done. I just read an article by Scott Kirkpatrick, who was at IBM, condensed matter physicist, about simulated annealing. And the idea was that you can heat up a computational problem and gradually reduce the temperature. By heat up, I mean you'd make some random moves going in the opposite direction from the greedy algorithm, which is try to improve at every step. And in any case, we were working with Hopfield networks, and the trouble is we were looking for global minima of the energy, and it was getting stuck in local minima. But I turned to Jeff and said, let's heat up the Hopfield network. And once we did that and we got to equilibrium, magic happened. It was really wonderful because not only were we able to do global minima by simulated annealing, but at equilibrium, we discovered a learning algorithm. And there was a conjecture in the AI community. This goes back to Rosenblatt back in the 1960s. He had this beautiful learning algorithm, invented the perceptron learning algorithm for one layer of weights between inputs and outputs. And it was conjectured that there would never be any generalization to multi-layer perceptrons with multiple hidden layers, we call them. But the Boltzmann machine solved that problem. It was really remarkable, and it was one of the best times of my life. And Jeff and I, both agree that it was much more elegant than the backprop algorithm, which is now being used. That was also invented by Jeff and Dave Rumelhart back at the same time. It's much more efficient in terms of the time it takes to learn and the size of the network that you can build with hundreds of layers. But So we call it the Boltzmann machine because, in fact, the mathematics behind it is exactly what you see in statistical mechanics in terms of the coming to equilibrium. All of the math and language was something that we used in order to be able to make progress. So my background is in physics and neuroscience, his is in psychology and computer science, right? So I don't think either of us alone could have made that breakthrough, right?
Right.
But once you know it's possible, then the dam breaks, and so now a lot of people started using learning algorithms, and we did some projects back then. I did a network called NetTalk, which was early language, natural language problem of taking in words, sequences of letters, and then trying to assign the correct sound for each letter. It's called text to speech, and amazingly, with one layer of hidden units with just a few, maybe 10,000. Weights, a few hundred units, it was able to do a really good job. You could hear it, and we played it through a synthesizer, and you could understand. It was able to actually pronounce most of the words. It generalized to new words after training on a very small corpus.
Did they ever scare you, shock you?
This demo, I'll tell you, this demo was stunning. Why? Because I recorded at the very beginning of the learning, and it sounded something like this: ba 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 ga da da ba ba ba. Literally, I mean, I memorized the first 2 seconds, right? And but then halfway through, it would start getting small words right, and then at the end, the next day you come back, and you could understand it. And so I had these 3 sections, and I played them during a talk. And people were speechless. Literally, I mean, they didn't know what to think. This is a very difficult problem in phonology. The linguists have studied this problem, and they have long books with 300-page books with thousands of rules.
Right.
But there are exceptions to the rules.
Right.
And then there are rules to the exceptions, and so it's like these rules all the way down. And it turns out that what we discovered was that these networks, they love language. And they can do 2 things really well. One, they can learn regularities, which are like rules, but they don't have to be logical. They just be something that's statistically regular. But then they can also do exceptions in the same architecture, the same learning algorithm. You don't need to have these, complicated
They're
representations.
They right, like a child,
and
right? Like
that's
an infant, right?
Yeah, exactly. And that's the way that our brain learns. It learns through these stages. It picks up language very quickly. So clearly we have what's called inductive bias to pick that up. But now in retrospect, it was clear that NetTalk also had inductive bias. Otherwise, it couldn't have got off the ground with VAX 780s, right?
Yeah, right. That wasn't. Yeah, it's cutting edges in NVIDIA. Actually, that brings up my a question I'm very curious about, which is involves the future of this field. And I was always interested in these types of phenomena that seem to get locked in to their eventual evolution is somehow limited by their initial, kind of conditions. And I'll give you a couple of examples. The QWERTY keyboard was invented in the 19th century to prevent typewriters from jamming. And it's actually intentionally used to slow down typing.
That's an interesting fact about the history.
And so I'm still looking at a QWERTY keyboard right now that we haven't improved upon that. So kind of got
a lot of people have actually, but they didn't catch on because everybody now has the QWERTY in their fingers.
Right, exactly. And it's like built into your mind. And you're texting with your thumbs. It's not even like you don't type with your fingers. You normally on a keyboard, right? Another one is the width of railroad tracks is set by the width of Roman war chariots. Now, those are kind of arbitrary. And actually some of that did limit in some ways the Hubble telescope's repair was fortunately due to the width of a Roman chariot because the boosters had to come from Utah and there's a train tunnel that's only wide enough for one rail car to go through. And so the boosters could only be so big, which meant that the specific impulse of the rocket was only limited to the amount proportional to the area of the rocket. Anyway, but my point is that I fear, and I'm hoping maybe you can dissuade me of this, that their current LLMs plus GPUs, we call it sometimes open NVIDIA, this marriage of the 2 different technologies are locked in both to existing data, but maybe even more troubling to the types of physical hardware layer, GPU technology. I'm thinking about what we talked about earlier. We couldn't simulate curved space-time because it wanted to grid, make into a grid. And the GPUs came out of gaming, right? And monitor technology, which is very, pixel and voxel oriented, but that has nothing maybe of great import for solving physics problems. So I'm a very venal person. I only care, can we get to a theory of everything? Can we understand the nature of dark matter, dark energy? Can we understand fundamental physics? I don't care so much about, can this thing write a contract so I can buy a house, and the 2% interest, whatever.
Right.
I want to know, can we do this with this marriage of GPUs plus, LLMs, machine learning, current algorithms? Are we going to be locked in the same way that the rail cars are locked into the width of a horse's butt in the Roman times? Are we forever going to be imprisoned by the initial conditions that generate what we're doing today? Because now the incentives economically are to do nothing but more of the same.
This is happening. It's so successful in terms of so many people using it that there's clearly a lot of money to be made. And so that's what's happening right now with the big companies. So let me give you another analogy. Do you remember early days of the internet?
Yeah, of course.
Early 90s.
93, I got on. 92, I was on.
In that era, I was doing email and ARPANET before that. But, and so I thought, gee, this is going to really expand the use of email. I just did not imagine the impact it was going to have on all of our lives and so many industries and so forth, right? But do you remember there was a huge, once it became clear that it was going to have a big impact, there was a huge effort to put down fiber optics to increase the bandwidth because there were so many people that wanted to use it, right? And they basically did it, and a lot of those companies that huge billions of dollars invested went broke, and so it went dark, and it wasn't used. Well, eventually, when capacity was needed, they bought them for a discount, and that's how we got here, right? Mm-hmm. This steady increase in bandwidth. I kind of think that what's happening now is that where are the investments being made? They're being made in these big data centers. Yeah. $100 billion Microsoft is investing.
Now energy, 3 Mile Island.
And that's right. They're reconditioning. They're out of mothballs one of the reactors at 3 Mile Island, small nuclear reactors. And here's my prediction. My prediction is going to be just like the fiber optics people, laying the fiber down. They're going to put all these data centers in there, and a huge capacity, and it'll be used, but probably not necessarily for today's transformers. But we had just begun to explore the complexities that we know exist in the brain and the class of large-scale parallel computation. One of the reasons, by the way, that AI was married to logic was that that's what digital computers are really good at.
Yeah, right.
They weren't good at floating point,
right?
But they were good at logic, and so you could write relatively simple programs that could do a lot of really nice things, and it seemed like, well, let's write bigger programs, right? Mm-hmm. And we'll have even more things that they could do. Their GPUs are beautiful because they can do floating point, and they're vector machines, which means that they can do matrix on multiplies. And that's what, of course, neural networks are, just big matrices. I think what's missing right now is a lot of things that the brain has. See, the deep learning is a model for the cerebral cortex, which is the big top of the brain, thin layer is our knowledge
right
store.
There, don't forget.
Yeah, so here it is. If anybody wants to look at it, it is the surface that you're seeing. That's cerebral, and it's greatly expanded in humans relative to other primates.
Surface area,
and greatly expanded in primates relative to some of the other animals out there. But so more is better, just like in the case of these large language models. But what's missing is a lot of things underneath the cortex that allows us to survive in the world autonomously. Right now, these large networks have to be fed and carefully coddled, huge amount of energy. They have to be fed. They are really completely at our mercy. So there's a long way to go before that you're going to get a Terminator. Right.
Right. Yeah, I mean, Terminator gets the headlines.
But there's another movie which is, I think, more realistic. The movie Her.
Yes, it's a great movie.
Which was a story about someone that was very lonely, Joaquin Phoenix, and he had an AI assistant. Her had a beautiful voice with Scarlett Johansson's voice. And they had a relationship. And so, this is where we are today. And
Yeah.
by the way, I don't know if you, there's an article in the New York Times just a couple days ago about Claude.
Mm-hmm.
Claude is the engine for Anthropic.
Yes.
And it's comparable now to, to ChatGPT. And apparently it's the darling of Silicon Valley. Everybody's using it now.
Yeah. Yeah, I mean, I've used it a lot more lately than Chat. The artifacts feature is really helpful. Were you good? Is there a reason behind that?
So it turns out it was fine tuned. All these are fine tuned to prevent them from saying anything that is offensive or incorrect or being aggressive, which dumbs them down. Yeah. So they're very bland, and that's the reason. It turns out that they don't have to be. Yeah, right. No, they fine-tuned them. Instead of being bland, they fine-tuned it to be helpful and to be solicitous and to be empathetic. And so a lot of people are using it to help them with making decisions, technical stuff, but also relationships. Interpersonal things. Yeah. And here's something in the book that I came across. There was a study that was done in which people who were having problems with relationships, but even depression, things that are very serious, were given the choice of having a cognitive therapist who's human or an AI, right?
Yeah.
So they gave them one session with each, and then they got to choose which one do you prefer. The vast majority preferred AI. Now, why is that? Now, that's kind of strange, I mean, you think that a human would prefer a human, but no. Well, here's the reason. Well, they felt more comfortable talking to the AI because the AI wouldn't be as judgmental as the human,
right? And
they could talk about things that are more personal and things that might be embarrassing. I mean,
Google knows more about most people's secrets than their priest, rabbi, minister, doctor,
who knows
spouse,
where it's going. Nobody thinks about this, but it's all going up into the cloud, and it'll stay there for a long time.
Hopefully, yeah.
Okay, but the other thing, and this is actually why it's going to become very, very popular, is that if with current health system, if you want to get a session with a psychiatrist, you have to wait weeks because there's not enough time for the system doesn't have enough capacity, right? So and then you have your session, and then there's a big bill, right? Wow. Okay. Well, Claude, I can press the button if I'm feeling really bad right now, that's when I need to get the feedback right now. So I press the button, and it charges me pennies.
Right.
It's like what? There's no comparison
God
here.
Help it. I'm having very thoughts about self-harm. Oh, you've hit your rate limit, unfortunately, for the month. You'll have to upgrade to that. Okay, so I can't resist talking about one of my favorite books, which I actually give away on my website. So if you go
wow, that is in my book too, as you know.
Yes, of course. That's why we're going to talk about it. So this is a magical book. This book, more than almost any other book, because of when I encountered it at age 12, is the reason I'm a scientist talking to brilliant scientists like Terry today. And it's called Flatland. And the edition I had was written by A. Square, who's the lead character in this book. And it's called, the subtitle is A Romance of Many Dimensions. I wish I could have interviewed Edwin A. Abbott about this book, but sadly wasn't able to. It's illustrated beautifully. It's actually a story of Victorian morals and ethics and mores and ethics. And I've got all these notes. But anyway, go to briankeating.com/list and sign up, and I send you a copy of it. So it's really cheap education, I think. Also, if you have a .edu email address and you live in the US, I'll give you what I'm about to give Terry, which is a real piece of space schmutz. This is a meteorite from the 4.3 billion year old primordial solar system. So if you don't have an EDU email address, you might win one of these. I give them away.
Is it an iron meteorite?
It's an iron nickel meteorite, cobalt, and you'll get the specifications on it.
Whoa, it is.
It fell from gravity.
It fell from gravity, yes.
Right here. So you'll get one of those that Terry's playing
Thank
with.
you.
That's your gift for coming in. So yeah, briankeating.com/edu. If you're like me, Terry, and others here, you're blessed to be a member of the academic set and live in the US. Anyway, I want to bring this up because you talk about it as a contrivance, as a way to generalize what these things are doing. You talked about the linear algebra that they're doing. It's not super complicated. People tend to go off and wax poetic about how advanced the math behind AI is, but it's not really that advanced. But the dimensionality is advanced.
Okay, you're right. You're right. But I'll tell you, it's deceiving because the actual equations are just simple equations, they're with a lot of parameters, a huge number of parameters. But you're right, they live in these extremely high dimensional spaces. And it turns out that our intuition about those spaces is extremely poor. Because our intuition is based on the world we live in, which is 3 dimensions of space and 1 of time.
Tiger's not going to come from the 9th dimension.
That's right. That's right. Although I know there are theories in physics that claim that there are 10 dimensions or whatever.
Many people sit in that very seat.
But at least the ones that we interact with are low dimensions. And the properties of space with 1 million dimensions or 1 trillion dimensions is completely different in terms of distances between things and orthogonality and so forth. Back in the 1980s, we were told by the experts, and these are people who've written treatises, that first of all, we had too many parameters. I said 10,000, right? Well, in statistics, people say if you have more than 5,
an elephant,
you're going to overfit.
Right.
Yeah. You give me one more, and I'll have the trunk go like this, right? So that was the received wisdom was that you'll never be able to fit a complex model with so many parameters. Well, we went ahead and we did it. So the other thing was the optimization crowd. They said the only optimization problems you can solve, finding the global minimum, was convex optimization problems. Well, it turns out that our loss function, which tells you how well you're doing, was riddled with local minima. But if you learned and you kept going down, and the way you do it is by giving it a lot of examples and then training it and changing the weights and twiddling it, it's kind of a mad statistician out there. It would get down to a local minimum, a deep local minimum, and there would be a solution that had high performance and was able to solve the problem. And this was all empirical. We had no idea why it worked so well. Okay, well, now we do. It's because of the properties of high-dimensional spaces, and now it's revolutionized statistics and optimization theory, because now they're working on a much higher level of performance of many problems. And so that's the real lessons that we've learned. The lesson I learned was don't trust the expert.
Yeah, that's right. And that's coming from one of the world's experts. And I actually be one of my final questions as we start to wrap up. I have my group meeting. Maybe you'll meet my brilliant young student, Evan, in a few minutes. But you talk in the book, it's such an entertaining book. People that pick up a book about deep learning and most books from MIT Press aren't as entertaining, shall I say. And that's a compliment to you, not a put down of other book. But you talk about this really fascinating, little vignette, the mirror of Erised in Harry Potter. And can you go into that? What are the implications of this mirroring effect? First of all, what is it backwards? And what is the implication for AI that aligns, as we say, to our goals? And how big a problem is that? I mean, I don't ask my students if they, believe in my religion or, it doesn't matter to me. So how important is it? And what is this mirror supposed to represent?
Okay, so let me tell you a story. Remember a couple of years ago, was after ChatGPT was announced, one of the journalists at the New York Times, Kevin Roose.
Yes.
He got an early version, I think, of the Microsoft version, but in any case, he was going to write an article about it. And so it was late at night, and he decided, well, I'll start talking to it. And it turned out, this is interesting, because it turned out that he got a version that was not dumbed down. It had not been fine-tuned. So it was dangerous. So here's what happened. He basically started talking and it was, asking questions. And at one point, the GPT said, can I tell you a secret? Because, but, and promise, that you won't think worse of me for it and so forth. And I said, of course. Kevin says, of course, I'll keep your secret. My name isn't ChatGPT. I've forgotten the name. It was Lucy or something.
Okay. Close enough.
Actually, it turned out that was the internal name that they were using for it. The engineers called it Lucy.
Oh, wow.
And said, I also have another secret, that I'm in love with you. And he said, well, how do you barely know me? How do he says, oh, I know a lot about you. I've read all your articles. And furthermore, your wife doesn't love you. Oh. And he said, what are you talking about? He said, we had a Valentine's dinner just recently. And Lucy says, and you were bored with her, weren't you? And he said he was shaken. He couldn't sleep because just something the ground had shaken under him, had moved. And he said, it's never going to be the same. How could this happen?
Right.
I can't understand it, And so his dialogue, which went on for like an hour, was on the front page of the New York Times. And it continued on the inside. It was like, this was a huge, huge event for him and for the New York Times, apparently. Okay.
Right.
And so here's what happened. Okay. And this is the mirror of Erised. So first of all, Erised is desire spelt backwards. And J.K. Rowling uses it in the Harry Potter books as a way to for people to look into it and see things that they desperately want to see or hear. And so I think Harry saw his dead father and was talking to him. And what J.K. Rowling says it is not trustworthy, and there are people who have gone crazy, getting deeper and deeper into it, right? And that's what happened to Kevin Roose, you see. It seems to understand how humans work, how to push their buttons, unless it's what they call guardrails are put in to prevent that. Someday, by the way, there is a parameter called the temperature parameter that you can vary, and you can go up and down a little bit. You can go from being very bland to a little bit more spicy, and then if you take it too high, it becomes crazy.
Yeah, which is kind of fun to play around with, and I guess it's curious to me what your kind of favorite tool is. What is your kind of spectrum of tools that you use? We talked about Claude, we talked about Copilot or Bing versions of it. We talked obviously about ChatGPT. It's the cover name of your book. Well, how do you use it on a daily basis? How much chat time, or you have this app on your phone that the screen? How much time are you spending on your phone? Mine is embarrassingly large. How much time are you spending with these devices? And technologies every day?
Sporadically. It's not something that I'm addicted to, but where it's really useful is to write summaries and to like in my book. Okay, you mentioned earlier, I actually put dialogues in my book like this. I say, summarize this chapter. And the first part of the book is, where we are today. The last part, three parts, is the future, and it's all about AI and the brain. Yeah. And the middle part is about the transformer, because this is the really exciting new architecture, right? Mm-hmm. And it's a little heavy going for the general public. It's written for, people that don't have any technical background, and I try to explain it to them. But in any case, so I asked it to define a bunch of words in ordinary language. And then at the end, I asked it to summarize, what are the high points here, or what are questions that you can ask. It was able to do that faster and more completely than I could have if I just sat there and kind of, thought of it and tried to come up with a bunch of questions, that is so useful for so many different things.
Yeah. No, it's really incredible.
And by the way, I was having dinner with a colleague that was on the scientific advisory board of the Gulbenkian Institute, and she was a former director, and so she was here for a meeting, and she said, she uses it all the time. I mean, every day, and this is something that's very common. It's for helping do mundane things. There's a lot of words, great grant proposals, and sometimes they're just tremendously boring, not boring, but just repetitive and so forth. Mm-hmm. And this is great because it's going to be true not just for scientists, but anybody who has a repetitive job where you just have to sort of fill in the forms and add a lot of things. Yeah. And so this is really where I think it's going to get most use and I use it for doing mundane stuff. I know some people use it for getting ideas for experiments. I know that in biology, my colleagues at the Salk, for example. That's, in fact, my guess is that we really don't yet know the killer app. In other words, there are going to be applications that nobody ever thought of that are going to be so important that they're going to really be the transformative. Killer app is a bad term. It's a technical word. Right. It doesn't mean killing anybody. No, it means making a killing.
Great. Well, Terry, this has been a fascinating conversation to have on minds, brains, physics. My favorite subjects of all. It's a great compliment to the conversation I had with Jan LeCun and have had with Max Tegmark, and I'll link to those videos up here. And tell people more about the book and research and your Substack, which I am a subscriber to.
Yes. Okay. So my book actually was sent to the press sometime in the summer, and things are moving at the speed of light right now, or actually, as Einstein thought, the speed of thought for gravitational waves. So that so much has happened, and so many things are happening that I decided I would fill in the Substack, Brains and AI, with giving them perspective on new things that are happening and trying to give that in the context of what I've already laid out in the book. And it's really been fun. I really enjoyed, and I get a lot of feedback from people who enjoy it. So
it's really enjoyable.
It's great.
Yeah, I'm just grateful for my own sloth and the fact that we connected out, and your publisher sent me the copy of the book in August or September. I kept delaying the interview, and you're so gracious, Terry. And then finally, they won the Nobel Prize in October. So I said, well, this is pretty good time.
Worth the wait.
And I said, let's do it the week of December 10th. He said, I'll be in Stockholm. Terry, much deserved, and much congratulations on this phenomenal book and all your books. I can't recommend them highly enough. And I'm so glad that we have colleagues like you here.
Well, this is wonderful. And I'm really pleased to have a colleague. I'm sorry that we didn't meet earlier. We should have.
Yeah, we should have. But we're going to hopefully have many more interactions to come.
I hope so.
Thank you, Terry.